6.1, Exploring Transformations. One of the main objectives today, we're going to talk about how to apply transformations to points and sets of points and interpret transformations of real-world data. Some of the vocabulary we're going to cover: transformation, translation, reflection, stretch, and compression. A transformation is a change in the position, size, or shape of a figure. What a translation is, it's a slide. It's a specific type of transformation. It moves each point in the figure the same distance in the same direction. For example, we're going to perform the given translation of the point -3, 4 and give the coordinates of the translated point. So if I just have a graph, how do I plot the point -3, 4? To the left 3, up 4. To the left 3, up 4. This right here is our given point. I'll just call it A. Point B is going to be translated 5 units to the right. So this point here is going to move to the right 5 places. 1, 2, 3, 4, 5. Do you understand what happened here? All we did is we took the point and moved it 5 places to the right. What is its new coordinate? 2, 4. The new coordinate is 2, 4. How about if I took point A and I'm going to make point C? 2 units to the left and 2 units down. So I'm going to move to the left 2, and I'm going to go down 2. It's telling you we're doing the translation from this point. So from the point -3, 4, I'm going to move to the left 2, 1, 2, and down 2. So I'm right here. What is it? -5, 2. What's really happening here? When I move it things left and right, what value changes? The x value, I heard. So if I added 5 to the right, I'm adding a 5 to this -3. For this one, I'm moving to the left. The left is negative. So I'm going to subtract 2. And if I go down, I'm also subtracting. So subtracting 2 from the y value. Another type of transformation is a reflection. A reflection is a transformation that flips the figure across a line called the line of reflection. Each reflected point is the same distance from the line of reflection, but on the opposite side of the line. For reflections across the y-axis, what's going to happen is the x-coordinate is going to change. If I had the original point of 1, 2, it now becomes -1, 2. It reflects over the y-axis. In general, if we have any x value, you make it negative. If it reflects over the x-axis, 5, 1, 2 again, the y value gets changed. Instead of being +2, it now becomes -2. We can transform a function by transforming its ordered pairs. When a function is translated or reflected, the original graph and the graph of the transformation are congruent because the shape and size of the graphs are the same. So if we do a transformation of any type right now, we're making an exact copy. We're making congruent figures. So here I have a graph of an M. What's the transformation we want to do? Translation 2 units up. So if I look, there's key points. One there, 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 and there. Those are the key points on that graph. If I take and translate each one of those points, I should get the same exact shape. Each one of these points has to be translated 2 units up. So this point becomes this point. This point becomes this point. This one becomes this one. This one becomes this one. This one becomes this one. Did I change the size of that M? No. Did I change the shape of it? No. The only thing I've done is taken the picture and translate it, moved it up 2 units. You can do it by looking at the picture, but sometimes you have a table. I don't have the table. If you don't have the picture, and we can make a table. My key points. This one here is -5, -3. This one here is -2, 0. This one here is 0, -2. If I want to move it 2 units up, which value is going to change? Which values up and down? The y value. The y value has to get added or subtracted. How many? So I'm going to add 2. So this one's now -5, -1. This one's 2, -2, 2. This one's 0, 0. You can look at a table and do a transformation, or you could actually have the picture and do the transformation. What's the 2 things we're talking about in this paragraph? Okay, pull or pushing, but there's words that go along with it. We're talking about horizontal stretch and a horizontal compression. What do you do for a horizontal stretch? I already heard push and pull. For a stretch, if you take horizontally, which way is horizontally? Side to side. If I want to stretch it horizontally, what am I doing going to be doing to the picture? I'm expanding it, I am stretching it. If I want to compress means you're going to push it together, you're condensing it. So you push together towards the y-axis for horizontal compression. For horizontal stretch, you pull away. When we're talking about a horizontal stretch, the blue line is your original one. The red line is the transformation. It has been pulled away. If you're doing a horizontal side to side, that's your x values. So your x values are going to change. If it's stretching, you're making the graph bigger, right? What operation makes things bigger? Multiplication or division? Multiplication. So what you're doing, if I want to stretch it horizontally by 2, you have to multiply the x value by 2. If I want to compress, that means you're making the x values smaller. So we're dividing, but we're not going to divide. We're not going to divide by 2. We multiply by half. Remember that multiplying by the half is the same thing as dividing by 2. If I want to compress it by 1/3, what would I do? If I want to compress it by a multiple of 3, what would you do? We're not going to divide by 3. We're going to multiply by 1/3. Horizontally, we mess around with the x value. Vertically, we're going to mess around with the y. If vertically you want to stretch something, you have to make the y values bigger. So you're going to multiply it by a number. For compression, if we want to compress the y values down, you got to make them smaller so they don't grow as fast. So we have to multiply by a fraction. And when I'm saying a fraction, it's between 0 and 1. Those are your basic fractions. We don't want to talk about numbers greater than 1. Because if I multiply by 1.5, is that going to make it smaller or bigger? Bigger. To make it smaller, it has to be less than 1. We're going to use a table to perform a horizontal stretch of the function y equals f of x by a factor of 3. We're going to take this graph here, yes, the little scribble, and we're going to make or give it a transformation of a horizontal stretch. What is the horizontal stretch going to do to this graph? How is it going to make it bigger? Horizontal stretch means left and right you're going to pull it across. So think of a rubber band. If you take a rubber band and you pull it horizontally, what happens? It gets wider, but something else also happens. It stretches here, but what about vertically? What happens too sometimes? So we're going to see what happens. Now, I'm not going to sit here and figure out every single point. We need a couple key points. I'll pick this point here, this point here, pick that one, and this one. Why don't I pick all the sort of corner points? They're not exact coordinates. We'd have to sort of estimate. It's 3.5. These ones I can tell. F of x is just a function. What's our first coordinate? 1, 5. What's our next one here? 3, 4. What about this one? 1, 2, and 4, 2. I'm doing a horizontal stretch by 2, correct? Horizontally, what number is going to change, the x or the y? The x. For horizontal stretch, the x value is going to change. By a factor of 3, am I going to multiply by 3 or multiply by a third? Which one stretches? 3 stretches, 1/3 compresses. The 3? In the example, it says by a factor of 3. Oh, sorry. I was thinking of the old problem. My mistake. So I have to take the x value and multiply each one by 3. So I'll multiply this by 3, this by 3, this by 3, this by 3. What's my new coordinate for the first one? 3, 5. So 3, 5. What about this one? 9, 4. Let's see, 7, 8, 9, 4. What about this one? 3, 2. 3, 2. And the last one. 12, 2. And I'm off my paper. It'd probably be right around here. Okay, this point became this point, right? So these two here had a line that went through, correct? And then this one, the line went below it, like this. And there was sort of a U-shape-ish type thing going there, right? We're sketching, and I'm not looking for perfection here. Yes, the graph doesn't look the neatest. I'm more worried about these points. Here's an example of a real-world problem. We have a cost of painting based on the number of cans of paint used. We're going to sketch a graph to represent the cost of a can of paint doubling and identify the transformation of the graph that it represents. If the cost of paint is based on the number of cans of paint used, and the cost of a can of paint doubles, the cost of painting also doubles. This represents a stretch factor of 2. I'm just going right into it. This is our original graph, correct? If the cost doubles, how much is it going to cost for one can? It's going to cost 100 instead of 50. What about for 2 cans? Instead of 100, it's going to cost 200. This one, for 3, instead of 150, it's going to be 300. You see the trend, correct? What has happened? It's going up. Now, if I took, well, what type of transformation am I taking? Is it a translation? Did I just take the graph and slide it up and down, left and right? No. Did I do a reflection? Did I flip it from one side to the other? No. So it has to be a stretch or a compression. Did it get bigger or smaller? Technically, the slope is now steeper. It is now a stretch. It has made it bigger. If the graph went lower, it would be a compression. So if we have recording studio fees, and say that we have a reduction in fees by 3/4 of its original rate, we want to figure out what type of transformation is occurring. We want to sketch it. So looking here, what are some of my key values? 3 is 100. So I have 0, 0, 3, 100. Give me another point. 6, 200. Actually, it's a little bit under 200. What's another one, if you can see this? 5 is 150. Do I have to do every single one? No. I need to pick enough that I'm able to draw the graph. With 2 points, can I draw a line? Yes. So I'll have 3 just to make sure. What did you say, 5, 150? Which one is talking about the rate? Is it your X or is it your Y? What's rate? If you work, you get paid a certain rate, correct? That's how much money. Rate is money. So which value is this? The Y value. So which one's going to change here? The Y. The Y value is going to be affected how? It's going to be compressed. Why? The rate has changed by a fraction less than 1. If you see a factor less than 1, you know it's a compression. If you see a number greater than 1, you know it's a stretch. What's 0, 0 become? This times 3/4. What do you get? 0 times 3/4 is 0. You have to think, if you don't go to the recording studio, how much do you pay? Nothing, regardless of how much it costs. If you don't go, you don't pay. How about for 3 hours? What's 3/4 of 100? 75. So if you go for 3 hours now, it's $75. I'll use this graph. 0, 0, board's not aligned. 3 is now 75. What's 3/4 times 150? What is it? 112.5. So 5's 112.5, it's right about there-ish. Take and draw your line. Did it make a huge difference in price? No. But what do you notice about the difference? Where is it starting to occur more? The higher hours, the more you're saving. Questions? How do you know you have a translation? How do you know you're dealing with a translation? When it moves, but what operation's happening? The x and y are being added, subtracted. How do you know you have a reflection? What's changing in a reflection? What flips? How do you know that you have a reflection? What's the dead giveaway? It has the opposite side, so instead of being positive, it's now negative. The sign has changed. For a stretch or a compression, the dead giveaway is you're always going to talk about a factor. By factor of something. You have to be able to distinguish, do you have a translation, a reflection, or stretch compression?